So welcome everyone. Welcome back from the poster section. And so our invited talk by today is by Ugur Kuter. So he is a research fellow at Smart Information Flow Technology. Many of you know, or either if not in person, through his work. He's been instrumental in the development of the shop line of HTN planners. He's created several HTN learning algorithms, extended hierarchical planning to handle non-determinism, incomplete methods, and so much more. And if you step outside of hierarchical planning, or may have published there too. He's worked in classical planning, cybersecurity, and even social network analysis. And if you browse through Ur's 100+ papers, you won't just find all these topics. You'll also see a diverse array of collaborators. And if you get the chance, you should really join that list. And if you do, you'll find a man who is diligent, warm, patient, and kind. Someone who understands that ideas need room to grow, and the thoughts in our head aren't always easy to communicate. So today, Ur will introduce a framework for collaborative, decentralized planning for heterogeneous teaming scenarios. And so please feel free to ask questions in the chat and afterwards, and enjoy the talk. Thank you.
Thank you, Ron, for that introduction. Hi, everyone. Thank you for coming today. So yeah, my talk today is about hierarchies in decentralized collaborations. And if I can find this is the slide I added. So 15 some years ago, Dana gave me this gift that, that jumps around like when you wind it up. And because my research at the time was touching different disciplines. And he was right. And what you see today is really nothing has changed all these years. So we'll talk about, a research line that we have at SIFT that touches a lot of research communities, and in particular, AI, human factors, psychology, some sociology, and other areas as well. So we are interested in decentralized collaborative environments in this line of research, and the goal here is we want to meet task demands necessary for collective goal and task accomplishment. The collective is the key word there. We just don't want to accomplish tasks, but we also want to emphasize teamwork, right? The agents, human or AI, collaboratively solving problems towards this given goals. In the process, the teams are being formed. They may be dynamically reformed, or they may be adapted, between these human and machine planners. And, if you look at really natural history of things, we've been doing this, all along. And, there are so many examples in the history, natural history in particular, as well as the research areas recently that involves decentralized collaborative environments. So one of the things that, I want to emphasize here is, when we say decentralized collaborative, the emphasis is really on the collaborative side of things. And that's because we do not, we're not focusing on in this research, the centralized planning or centralized thinking, where you generate a plan and then that involves roles or actions for multiple agents that might be involved, and you push that plan to the agents, and the agents execute that plan in a decentralized fashion. So we are not doing that here. We are truly trying to think planning and execution in a decentralized fashion. And planning could be pre-execution as well as in execution, although I'm not going to talk about execution side of things today that much. Yeah. And this slide is just showing like so many examples, so many difficult scenarios inspire from the nature, as well as we started to get these scenarios, understand these scenarios, and use them in our AI-based systems like UAV farming, for example, or like simple carrying a package with multiple UAVs. So what is collaborative teams? We are focusing on large networks of heterogeneous agents that can coordinate and rapidly distribute themselves. Now, these agents can differ not only in terms of their roles. So when we talk about like these teams, we're not just talking about organizations, but they can be heterogeneous in terms of their capabilities, in terms of the resources they can control, and the things that they can do in the world. The perception of the environment is therefore collaborative. So it's not, so we're going to come back to this. Typically, we're not going to assume locality, properties here. And the decision making as a result of that has to be collaborative and decentralized too. Now, one of the key assumptions that we're going to start with here is communications, is about communications between these agents in a team. We're not going to assume full communications at any time. We're not also going to assume that, these agents can observe each other and, from the observation, they can recognize their behaviors. Although these are very useful capabilities, but in some of the real world problems that we're interested in, that I cannot speak today, at least as they are, these assumptions do not hold. And furthermore, the planning side, the thinking, if you will, in these teams, is for existing entities and organizations. So we're not going to assume that we can go in there and write a domain description to solve the problem. For example, some parts, and in some cases, most of the parts of our domain description, domain knowledge is already given in a way. So with this setup, so how are we doing this? Really, how humans have been doing this? Really, how did we get from hunting mammoths and collaborative AI teams that we can perform surgeries with robotic systems? So my argument for this, for an answer, a possible answer to this question is really hierarchical organizations. It's not just organizing the agents, organizing the teams, but organizing hierarchically the mental models behind these teams, functionality, skills, and more importantly, the knowledge, that all these agents that possess and use and share. And how do we, really organizing that knowledge in a way that, enables us to do, for example, to be very robust to communications loss, to be very robust to, bringing somebody new into the team and, taking somebody out, and things like that. And really, if you look at, the literature, this was right there when the early days of AI, when the researcher was talking about the AI in the early days, right? This is Minsky's, for example, Society of Mind. And, the first chapter, one of the first chapters, when he was talking, even the Block's world, he was talking about hierarchical organizations of the knowledge of the world, from the agent's perspective, especially. So we would like to, continue with this trend and, set up a framework that, that we can apply into the real world problems that we have today. One of the things that we started with, in our design of this framework is something called naturalistic decision making. This is originated in psychology, and it's a means of studying how people make complex decisions, cognitively complex decisions in crazy complex situations. You have limited time, you have uncertainty, high stakes, organizational constraints I talked about, very unstable conditions. Things change, unexpectedly, you know, all the time in the world. And we have varying amounts of experience between the agents. So the kind of the architecture diagram, abstract diagram over there is from this work. I mean, it's not our diagram, but it summarizes, it's a very good summary of what we can do with the current state of technologies that we have in AI right now. And if you look at this diagram, for example, you can see a lot of these boxes, we already have algorithms, good algorithms for this. It's just that the diagram puts everything together. Now, when we put everything together, we will see more challenges, the new challenges that are arising just because we try to, use these algorithms together. For example, the mental simulation of actions. You can use planning, you can use search, you can use other algorithms there. Recognition, plan recognition has been advanced. There has been so many advances in plan recognition that can be used there. Expectation-based planning, one of the things that we're using, we're kind of extending, generalizing there is, this Ra Kambambati's notion of expectation-aware, human-aware planning there. And, there are a lot of works on seeking information gathering, whether we know our states of the world correctly, how do we deal with uncertainty with the world. Of course, the diagram is designed for a single agent, right? I mean, this is one agent's mind, if you will. When you add multiple agents, when you add a decentralized system collaborating together to solve a problem, a lot of these boxes gets very, very complex, because it's not just like one agent thinking about the world, as you can see. Now that agent has to think about the world, but think about his teammates as well. In order to do that. Remember, we're not doing centralized planning. We don't have a centralized mind, a Borg, if you will, that controls a bunch of drones to achieve the goals. We're trying to get to a decentralized collaboration framework. Now, with this in hand, from psychology, our very, very, very biased starting point was hierarchical task and goal representations and planning, of course. Why? Because we know how they work. Most of us in this group has worked in this topic, and they provide very expressive representations. Now, expressivity is good because real world is complex, right? I mean, we need to design very complex knowledge for dealing with problems in the real world. Well, expressivity is bad because when you want to verify the knowledge, when you try to understand what this knowledge is going to do to your agents, especially when you have a decentralized system, when you combine these pieces of knowledge, if you will, and we're going to talk about this a little bit. And we have so many existing now, thanks to great work of this community, existing representations and planning approaches from everybody all over the world. So that's great. And in this talk, I'm not going to talk about one particular existing representation, although I just said that, we are using HTN kind of formalism. But I'm going to try to keep it abstract and talk about the problems and the challenges instead. Now, different hierarchical knowledge formalisms are primarily used for, in the past at least, for different search control pruning properties. So this is great. And, I didn't have a chance to, really to put every result here. These are some results from our work with SHAP2 and SHAP3 planners right now. Yeah, sure. I mean, search control, we've shown this. It works better than classical planners. We can encode different kind of problem-solving strategies in the domain descriptions, and that works well. And if you put this in a decentralized framework, that's great. I mean, because decentralization, for example, in the bottom right there, decentralization provides parallelization. If we can have sub-goal serializations, for example, those kind of properties in the problem, and generate problems where they can be solved independently, decentralization is great with these kind of planners. And you can use the hierarchies to do that as well, to dynamically plan for those sub-goal serializations. So this is all good. But the question we really wanted to ask is, what's out there beyond search control, pruning, or selection mechanisms? We started with the claim that hierarchical knowledge defines a process space. So by that, I mean that, typically when we define our domain descriptions, we put our task decomposition methods, operators and all that. That domain description itself is essentially an Endor graph in general. It's not a solution tree, right? I mean, when we use the hierarchical knowledge in order to generate a plan, then we generate one particular solution tree in that space. So one thing that we were interested is, how can we make use of this Endor graph in general, rather than just use the knowledge to search? When you start with that, we realize that that kind of knowledge essentially provides a great deal of explanatory and information from the domain that you're working on. So we can talk about, different planners. We can talk about what one planner wants to do, other planner, in the team. We can talk about alternatives during the planning process. It's not just like searching one alternative and backtracking, back jumping to another if something fails, but we can explicitly reason about those alternatives when we are making decisions. And we can explain why we made certain decisions, over another in that space, and how we generate the plan. So these why, what, how, and who questions turn out to be very important for decentralized collaborations. And we have the tools, it turns out, in our hierarchical knowledge representations today to address those questions in that problem. So here's another example I mentioned. Instead, like, when you're actually talking about alternatives, when you're seeing the Endor representation of your domain knowledge, not just the search knowledge, but as your space, process space, you can think about counterfactuals in planning. It's a very natural way of saying that, okay, I'm going to follow this leftmost red a branch, for example, in order to get to the H node, which could be a plan, which could be a task. But then I can also think, why didn't I choose something? Why didn't I choose G? Why didn't I choose H? So if we can record that knowledge, we can record the answer to that knowledge, and that could become heuristic information, or it could become plan repair information if you're doing dynamic plan repairing or replanning later, or we can just communicate that to other teammates, human or agent, AI agent. So the knowledge of the Endor tree seems to be, we found out that it's powerful, and it gives us a lot of information to use beyond search control to generate a good plan, essentially. So we exploited this, and this is just a distraction slide that I stick in there. It's not only the knowledge organization that can be hierarchical, but it turns out that if we reorganize our algorithms in a certain way, certain design ways, then that really helps too, in terms of decentralization and collaboration and this notion of teaming. This is from SHOP 2 to SHOP 3. one of the things that we've done is essentially we took the algorithm, the implementation algorithm and the design of that algorithm from a recursive backtracking search algorithm. We turned it into a state machine, the algorithm itself. Now, once we have that, basically it's the same algorithm. The inputs outputs are exactly the same, but we can modify this state machine, and we can explore different paths inside the algorithm given the situation more easily than just a recursive design of this algorithm. And it turns out that it solves problems that SHA-2 for example couldn't solve, mostly because of memory constraints. It just uses less memory in that sense, and it's faster, better, and cheaper. So as I said, it's a kind of a distraction slide, but it helps us a lot because we can add new boxes here, following good old modular programming perspectives as well. But we can add new boxes here, new capabilities very easily in this kind of organization. So it's not just knowledge, your design of the algorithms matter too, when you use that knowledge. But going back to the knowledge, one of the things that, it's important in decentralized collaborative planning is this notion of shared mental models, process models, shared knowledge, if you will. So the team performance basically, especially in high complexity, requires, different mental models, different knowledge sets. But if the team members overlap in their knowledge, or even use the same knowledge, domain descriptions and knowledge sets, it turns out that essentially one thing you can do is, one agent thinking in the shoes of the other agent, during execution, especially if they cannot talk to each other, especially if they cannot observe each other. Basically, a look-ahead capability, if you will, through that knowledge graph to see what alternatives this other guy might be thinking. What alternatives, how is it going to achieve its goal, really? So I can adjust my plan based on that constraint, if you will. So one thing for that, what we are doing here is, we defined in our hierarchical representations a way to share, resource models, the hardware, the platforms, whatever cameras you might be using, the task models, team interaction models, that this can be encoded as hierarchical knowledge because it's very natural, since human societies, any kind of societies are typically hierarchical. So roles, responsibilities, who's providing what information, comms channels, and interdependencies. So, and the team model itself. And so we found hierarchical representations that we have in planning are incredibly capable of modeling this kind of domain knowledge as well. And it helps. It really helps with decentralized collaborative teams, human and machine mixed in that sense. And it's something that it's harder to do in action-based formalisms like PDDL. You can still do some of this PDDL. For example, you can share the heuristics that the agents might be using, but it's hard to reason with those heuristics. If I need to go in there and solve problems and reason about what else this guy can do, what alternative behavior it can execute, for example. So this is a very abstract example of these mental models for decentralized nodes. So as I mentioned, if you have a bunch of planners here, if they share the hierarchies, the Endor space, if you will, then we can do task goal handoff between these decentralized planners very easily. We can do dynamic team formation, expectation-based collaborations, and look at and spare reasoning. Just because we have this shared common scaffold, if you will. And here is an example there. So for example, here the planner one could be the higher level strategical planner, basically sets the problem. It can send those problems to the other planners. The other planners can just generate their lower level plans and then send it back. There is and in execution, composition could be done in planning. For example, everybody responds back to planner one here, and then planner one compose the solution tree, sends it to execution. But also composition could be done in execution without explicit planning necessities, because everybody knows their constraints, everybody knows their boundaries, everybody knows what they're going to do, and maybe one planner has the bigger picture. So there may not be, in some situations, there may not be a necessity for explicit composition of the plans. You just execute and things work. Now, I mentioned here and there about the communications problem assumption that we've been interested in. So we all know how communication is supposed to work. Assuming that we have full communications, everybody talks whenever they need to talk and share information is great. It simplifies the world, but it's not how the world works, really. Even we can talk. Even these agent talks, there might be misunderstandings. It might be because they are not looking at the same state. It might be because one of the agents is human, one of the agents is an AI. They are not really talking about the same language necessarily. So we found communication, especially these complex, plans, complex ideas, is difficult. It makes a lot of things difficult in the sense that we need to design systems with this in mind. If you throw a system, after the fact, and the communications become difficult, then it could be a problem, depending on your domain, depending on your scenario. So we started with this premise, and we started to develop a framework that we called Arcade. This was first appeared in IAAI a couple of years ago, and it's a service-oriented, agent-based, service-oriented, decentralized architecture that uses certain communication protocols for the agents to share information during planning and execution. Initially, we started with HTTP because it was cool, mostly. And we showed that actually we can put planners all over the place, like all over the world, and they would be able to generate plans, they would be able to solve problems talking over the internet. And that was interesting because, when you have internet, you have natural communication problems. You have latency issues. You have packages being dropped, things like that. So that was an interesting challenge. And at first, to let us know essentially, what kind of things can go bad in this kind of a framework. And we do not necessarily assume a fixed communication network topology. Agents come and agents go, essentially here, or, teammates come and teammates go. If, for example, here, the San Diego agent on this map, on the West Coast drops out for some reason, we can bring in some other guy, some other agent from some other place. Of course, assuming that they have shared mental models and they are filled in with the right kind of state information for the task, they can pick it up and then, start planning and execution there. So so this is the framework actually we've been using, and we apply this since 2019 to very different kind of decentralized collaborative problems. And one of the things that that came up with this framework is this notion of information locality, or rather lack thereof. when we design a planner, typically, we assume that, I've been assuming all along that before this line of work, that the information and the knowledge that the planner needs is typically in one place, right? The planner has access to that place. The planner can do whatever it does with that knowledge, generate plans, execute. Well, that doesn't hold with the decentralized collaboration stuff. I may be seeing things, or I may be reading a paper that you haven't read so far. So the information I have and the decisions I'm making based on that information, if you're, for example, collaborating on a new paper, is different than yours because you didn't read that paper. Now I can give you that paper and let you synchronize, if you will, with that kind of information. And that's one of the things that we are doing in this framework. Or I can just summarize that paper to you, or I can assign only specific tasks to you that doesn't require that information. So so we are looking at all these locality situations where locality doesn't hold, essentially. And this is a quote from an Australian British philosopher, who basically says that if you decentralize like this, you actually have more information, you have more capabilities. So that's been fun to think about when we were designing the system, based on against this locality assumptions. And one of the things that that came up with when we're thinking about locality is, okay, what are we going to share as an information? We assume that we have the knowledge shared, but in terms of information, what are we going to share? What we settled down is essentially objects and object types as a powerful entity that we all have, all have access to in the world. And most of us in a team have some sort of common knowledge, even if it is not explicitly elaborated in our formalisms of state or planning knowledge. Objects carry some intrinsic semantics that are kind of common knowledge to everyone. Not everyone, but most of the people. Now, for example, if I show broccoli to my kids, you're going to get those facial expressions. Everybody reacts, at least in my house, to broccoli like this. But if you show pizza, I mean, everybody is happy, right? I mean, so it's good. So the idea that we try to design, and I design a concept from this idea, which is straight to cognition, right? To use objects and object types to communicate, as well as to collectively plan, and reduce the need of this continuous communication. If I'm making a pizza, you guys know pretty much what you're going to get out of that process, right? Well, I can tell you more that I'm going to bake a pepperoni pizza. Then you have more information what kind of output you're going to get from me, or how am I going to do my task. So I don't need to specify the entire planning process or entire planning plans themselves to give you that information. You can still continue your process based on that assumption that you're going to get a pizza. And it turns out that it is useful to use these kind of entities, entity information and the relationship between entities during decentralized planning. Now, if you want to formalize this, we can probably formalize some of these in first order or subset of first order logic, the typical predicate or propositional representations we have. But then you're using the ability to explicitly reach in to the formalism and talk about the objects, and communicate the objects that way. At least you have to do some sort of translations or some sort of processing to get there. So this is more directly communications of those intrinsic semantics. But the objects, isn't the end game, right? I mean, it doesn't answer all the questions. If I cannot communicate, for example, then what am I going to do? Like I can weigh my broccoli all I want if the other guy doesn't see that. So one of the problems actually that we faced, and this is just one problem here, is objects created at runtime. So when we have plans, when we have decentralized team doing something in the world, they may create objects, right? So for example, you stack the blocks in a certain configuration that you call a staircase at the end. Now you can explicitly refer to staircase without that block building process. But then, if the other guy doesn't know about the concept of staircase, he has no idea what you're talking about. So this become an issue for us, and we don't have a good solution to this yet. So for example, these are some examples, and this is probably the only slide that you're going to see some implementation representation examples here. If you're delivering a package here, we may have a looping behavior, an iterative HPlan method. I'm a big Lisper, so in HPlan, in SHOP3 formalism, we designed our iterative methods in as loop macros in Lisp. So apologies for that, not an abstract representation really. But essentially the idea here is you're looping over some the trucks and the location of the trucks, and for each truck you're preparing the package it needs to carry, and then you may call a logistics plan, to plan that the lower level actions that truck needs to take in order to go from one location to another. But the package itself is generated in the runtime. Right? There is no package in the initial state, package one. The package may contain all the items that you ordered from your favorite, online retailer. But the runtime generates package number one, or some order ID. So how are we going to deal with that, really? How are we going to, from a single planner perspective, there are ways to deal with that. For example, one way is to use scalumization. We can generate scalumized functions or constants to refer to packages and use them consistently along a single planning process. But when you generate a scalum constant, everybody needs to know what that scalum constant refers to, essentially. So that has been a challenge, and we don't have a good solution to that challenge yet. The other challenge is, the loops, recursion, and the dynamic methods that we can use in our hierarchical representation and languages is really, really hard to explain, because just by looking at this looping method, and the method on the bottom is not just looping, it also defines the hierarchy beneath it in the runtime. The loop there gets a task list as a parameter. We don't know that task list is parameterized yet, and then iterates over that task. Essentially, the plan iterates over that task dynamically. So how are we going to explain this, even if we have the Andor graph approach, without knowing the task list, right? So we can anchor our observations, our knowledge to that task list, but that task list might be changing during execution too, because some of the tasks might be failing, for example. So this kind of expressivity is super for planning. We can really model very complex domains and problems with this kind of hierarchical expressivity, but it's hard to explain, hard to deal with when you're talking about collaboration to work together. So these are some open problems for us, at least, that we're working on these days, and it's been a lot of fun, but it's been a lot of challenging situations as well. One of the things that, that also, showed up in this line of work when we think about decentralization, collaboration, especially when you don't have comms among the planners and the agents, is what I like to call ghosts in the machine. So I'm a big Asimov fan. Ghosts in the machine is not like an Asimov term per se. There are other philosophers, there are other sci-fi authors use the term. But this is from iRobot, the movie. If you remember the movie, Dr. Lanning here talks about ghosts in the machine, where the example is, when you put the robots in a container in a dark place, they get together. They stand together. How do you explain that behavior? That behavior is not nowhere in your knowledge base, in anybody's knowledge base. But when you compose the pieces of the knowledge, arbitrary pieces, arbitrary looking pieces rather, those pieces coming together during execution in particular, it actually, you observe a certain behavior that you didn't expect from the team, from the group of agents. One easy example of this is, again, thinking hierarchy, not just like flat groups. When we have group of less knowledgeable planners supported by a more knowledgeable, more capable planner, then the more capable planner can, observe this behavior, even though the other planners have no idea what they're doing. I mean, they have their own goals, they have their own tasks, but they don't have the big picture. And we can recognize these emergent behaviors. Now, these emergent behaviors can be good, because if we recognize it, then we can encode it as a piece of new knowledge in our Endor space, process space, and we can intentionally use it in the later episodes. The bad thing is, of course, this knowledge can surprise us. We don't want that, so we need to put some safety guarantees, safety constraints, if you will, against certain things that can emerge that we don't want in our teams. But this has been a lot of this has been a really interesting challenge. And here's an example, right? I mean, the two cooks in a kitchen. One of them is doing grilled chicken, the other is cooking pasta. They haven't communicated. They didn't talk before. These are the resources they are doing. All they know is they need to do these tasks and put them together. Well, when you put them together, you get chicken parmesan, but you don't have a chicken parmesan, HTN or HGN or whatever hierarchical method, if you will, to do that recipe in your cookbook. So a capability to recognize that, in this case, a human observer can know about the chicken parmesan, and use it as a recipe in your book, actually helps us, because the next time you suddenly have a new dish to serve, not just grilled chicken or tomato sauce pasta. So these emergent behaviors, when they use intentionally in decentralized teams, actually we found out in some of the problems we're dealing with are, this kind of sources of surprise and creativity, you may call, in the behavior of the decentralized system, which has been very interesting, because that's what humans always do. When two grad students sit together, try to write a paper, suddenly, some new ideas come out that nobody talked about, right? I mean, that's how you got your dissertation. So it's fascinating to see some of these behaviors actually emerging with the hierarchical organizations we have. And as I mentioned, the surprises and ghosts, we can, in our work, we're characterizing them, surprises, okay, I expect one behavior, but in our Endor space, this guy, my collaborator, did something else. Why? Right? I can explain that why, and furthermore I can explain why not. Right? Why didn't my collaborator do this other thing that I was expecting? Ghosts are completely novel behaviors. Right? The Parmesan example, for example. We can still learn these behaviors. We can still recognize these behaviors and use them in future episodes in our systems. Now, this all brings us to a different kind of uncertainty. that decentralized collaborative systems needs to deal with. Traditionally, our localized planning, when we have information locality, when we deal and model with model uncertainty, we model it for the world, for the physical world. Non-deterministic domain models, MDPs, or what have you. Basically, we think about expected outcomes of the actions rather than unexpected outcomes of actions. Those expected outcomes of actions will most likely be incomplete because we cannot enumerate everything in the world. And there are, but when you think about the unexpected, there are too many unexpected outcomes to enumerate. So how to deal, and you lift this knowledge, this uncertainty reasoning now, not only to the knowledge level, because we're dealing with our endorsed spaces, but also to a decentralized, framework. You're not only reasoning about, like, if I pick this block up, I may drop it. You're reasoning about that. What if Ron picks that block up and then he may drop it? How is it going to mess up my plan, right? So it just like blows up the complexity. And there are ways that we can approach this problem. In our work, found explicit state representations to be a little bit not usable at first sight, at least because of this uncertainty. The more compact representations, such as BDDs, ADDs, are more useful, but we haven't really tried them in this decentralized collaborative settings. How to describe a BDD that makes it easy to extract this information from the compact representation is the challenge, is the question. Instead, what we chose to do is dynamic plan repair, very quick, real time, in execution, not replanning, because we want to repair the knowledge so that we can explain it, right? We can communicate it. But also, hierarchical learning and knowledge capture algorithms that we have to deal with this. So the learning one, this is kind of an early work in that series of algorithms, what we call hierarchical abstraction learning some time ago. The idea in this project that this algorithm came out to was, we took a Java program, well, a subset of Java program. It turns out that we can actually translate it into an HTM. A limited translation, of course, you cannot, one-to-one. But if you do that, then you do an HTM planning and learning on the HTM representation, and you can transport it back to Java. Now you're writing programs pretty much online, as at the source code level. So we are using this technique, which learns hierarchies from data flow models, like how the objects, how the parameters, how the values are connected to each other, not the predicates necessarily in the state. And how from that data flow models, how we can abstract them into a hierarchy and, fill in the gaps, if you will, in your domain knowledge sometimes, or learn new methods, if you will, or adapt your knowledge and generate a new plan. Once you can adapt your knowledge that way, you can just replan very quickly because you're working with a subspace of your process and/or graph. So it turns out that this kind of learning is actually a good approach for our problems, at least for dealing with uncertainty in a way. And hierarchical repair, again, I'm not saying replanning because we aren't necessarily interested in from generating a new plan from whatever current state we end up in to a goal state we're trying to get to. Instead, we want to work with this Endor graph and find plans or plan snippets within constraints in that space. And this has been, a line of work that we've been doing over the years that we're just using, to be honest, in our systems right now. And again, here, when you do the hierarchical repair, the reasoning about the options is natively in there. I mean, you're not just doing state space search. You're working with the hierarchy in order to patch your plan, if you will, against a discrepancy. And most of the a discrepancy here can be a state change, something unexpected in the state, and your action failed, or world blew up or something. But it could be that something that your teammate did really didn't fail anything, right? But it was an unexpected move from your teammate. Why did he do that? How should I adapt to that? Because we're trying to be stable in the team as well, and to achieve the goals, not just like selfishly do our goals, right? And we have some experimental results that shows in some situations, some domains, some of them are IPC domains, that repair works faster at least than replanning in some setups. And the stability of plan repairs has been crucial for us, right? So by that I mean that when we change our plan due to a change in our surroundings, we do not want to trash everything that we've done before, right? That creates a lot of surprise, a lot of uncertainty for the others. What we want to do is we want to minimally perturbate what we're doing while addressing the disturbance, while addressing the discrepancy we believe it's there. So, so plan stability in that sense has been a very important concept from the beginning in this decentralized collaborative teams. And of course, we are doing SHOP, and we need to come up with an acronym that uses SHOP. Our planner for this is SHOP Fixer, which is based on SHOP 3. And it seems to be, at least in some preliminary experiments, it seems to be performing well compared to other repair algorithms. In this case, LPG, classical repair algorithm from Maria Fox, and their stability notions in these repairs. So to conclude here, really we started with this notion of this naturalistic decision making, and we found it is a very powerful concept, even though it stemmed from psychology without thinking how AI is designed, how logical formalisms are designed, and hierarchical representations and organizations serve as a really good foundation for this notion of NDM and its use in decentralized collaborations. And I'll just put this slide up while I think taking questions. Where are we going with this? Really, where I want to go with this is the concept of mind. If you go back to Society of Mind book, Marin Minsky's book from 60 years ago now, they all and others as well as argue that mind and body are not connected, right? Are connected. Unlike, like ancient Greek models of mind and body, like of Plato or whatever. And decentralized collaboration, if you think about it, is not really different than human body. In human body, you have so many different functionalities working together in harmony, collaborating for certain goals at certain times. And really, we can use these works, these philosophical, works, essentially as a model to design our maybe next generation AI systems. And one of the questions that keeps me awake at night sometimes is, when does mind or self-awareness emerge from this decentralized collaboration? Ghosts in the machine is perhaps like a one step towards that. But when do we know that the systems are self-aware and can do things by itself without being taught, without being given knowledge, for example? So with that, thank you very much for listening.